Now watch this question. This is asked in GATE 2000 2006. This is asked in GATE 2006. You can even read the question there, or I have written the question for you. Let me read it out and explain. Consider the following snapshot of a system running n processes, which means that they are saying that when the system is having n processes, they are stopping the system and examining the system at some point in time, and that is what it is, the snapshot. And now process I is holding xi instances of resource R. They are saying that process I is holding xi instances of resource R, which means there are I processes, right? So there are totally n processes, and out of which I is holding xi, which means every process pi is going to hold xi instances of resource R. For I, 1 is less than or equal to I is less than or equal to n. It is nothing but they are saying that p1 holds x1 resources, p2 holds x2 resources. That is what they said, right? And then currently all the resources of R are occupied, which means how many ever resources you have of type R, they are all given away, which means there are no resources set. There are no resources more. So n processes have taken some part of R in such a way that all the processes have taken up all the resources. Therefore, there is no more instance of resource R, right? That is the meaning of it. Further, for all I, process I has placed a request for an additional yi instances, which means every process has taken up xi instances, and even they want yi instances more, right? There are exactly two processes p and q such that yp equal to yq equal to 0. It means that all the processes want even more resources to complete, but only two processes are saying that we are done, which means we don't need any more resources. We could work with whatever resources are given to us. What are the resources? xp and xq. Which of the following serves as a necessary condition to guarantee that system is not approaching the deadlock? Okay, fine. So in order to answer this, maybe you need to understand this question with an example. That way it will be easy. See, later we shall examine about this banker's algorithm. There this question will be even simpler, but the reason why I have taken it is since we are talking about one resource and then many processes, it will fit here. But if you didn't understand this, again you will understand it later. So I'm going to try my level best to make it clear and simple. And even if you don't understand it, please finish this entire series of lectures. Definitely you will understand. Okay. For now, let's see the example. What I mean to say is, this example is like this. Assume that I have totally number of resources are 10, and there are three processes P1, P2, and P3, and say let's not write this yet, and assume that P1, P2 and P3 requires resources like this. This requires 5 resources, 4 resources and 6 resources in total, right? And say we have 4 plus 3 is 7, 7 plus 5 is 12. Okay, so say we have 4 plus 3 is 8. Okay, 8 plus 7 is 13. 8 plus 5 is 13. Okay. Say we have 13 resources. 13 resources, there will be a deadlock. 14 resources. Okay, and now assume that at some point of time the processes, they got assigned the resources like this. This one has got 4, and this one has got 4, and this one has got, it is 8, and how many are remaining? 6 are remaining, so I could even give it 6. So let's say a different number. Let us assume that the way in which the processes are is 4. Let us say 2 plus 4 plus 3. 2 plus 4 plus 3 is 9. Okay, fine. Okay, let us say the total number of resources are 9, and the requirement is like this, right? And say at some point in time the process have taken the resources like this. This one has taken 3 resources, and this one has taken 4 resources, and this one has taken 2 resources, and all the resources are over, right? and now how many resources they need. This is what is allocated, which means they are all already holding this, and how many resources are remaining. The number of resources remaining are here, how many resources are required. So extra resources required by each process are here 2, here 0, and here 4. Okay, fine. I think I came up with the right example. Okay, now that is what it is. So they are saying that at some point in time we have these many resources allocated, and this is a request by each process, right? And all the resources have already been allocated. If you count this, all this, it is going to be 9. All the resources are already allocated. So now, do you think that it is going to lead to deadlock? Just think about it. It might not lead to deadlock. The reason is, whenever you have allocated, see, process P2 needs 4 resources, and you have allocated all the 4 resources, and at this point of time the 4 resources are with P2, but later after some time what happens is P2 is going to release all the resources given to it. So after some time P2 will finish its execution and all the 4 resources will become available. So after some time what happens is these 4 will get released, and these 4 can be given to either this one or to this one, right? Understood this? But then don't give 1 here and 3 here. Anyway, what I am trying to say is, once the process finished execution, whatever is allocated to this is going to be released. Why is it going to be released is, it does not need any more resources to complete. Therefore, it is definitely going to complete without any request of resources, right? So this is going to be available. Now, if the available resources, which are 4, can serve to at least satisfy one of the need. It is a need, right? This is the need, and the need of this one is 4 and the need of this one is 2. Now using this one, if we could at least serve one of the need, definitely there is a chance that we might not go towards the deadlock. See, and in case, let us say this one needs 2 resources and this one needs 4 resources, and now we got only 1 resource available after this, then what happens? This one cannot be satisfied or this one cannot be satisfied. In this case we can say that it definitely is going to be deadlock. But in case if I have 4 resources, and using these 4 resources, if I can satisfy either this one or this one, any at least one of the process, then there is a chance that I'm not saying it is sure, then there is a chance that the deadlock might not occur, right? So what is the meaning of it? Whenever you allocate all the resources to the process, and after executing the a process after getting executed, if it is going to give you some resources, using those remaining resources or whichever you got, if you are able to satisfy the need of at least one of the process, there is a chance that the deadlock will be broken. In case using these resources, if you are not even able to break the if you are not able to even satisfy one of the needs of the process, then definitely there is a chance of getting into the deadlock. So what is the necessary condition? Necessary condition is, whichever process finishes and whichever process gives you the residual that resources, that should be able to satisfy at least one of the process needs. If that is happening, then what happens is, if it satisfies at least one of this, either this one or this one, then what happens is, once you satisfy this process, this one will also give you the 3 resources. Then you can add them, and then you might be able to satisfy some other. Otherwise you will get stuck here itself, right? I am not saying that there will be no deadlock, but then there is a chance that if this happens, if you are able to satisfy at least need of one process, then you can collect even more resources and add to the pool of available resources, and using this you can satisfy the other needs. I am not saying that it is always true, but then if this condition doesn't hold, you will never be able to do it. You will not be able to break the deadlock at all. In case if this condition holds, which means using the residual resources, if you are able to provide service to at least one of the process, there is a chance that you might be able to break the deadlock, isn't it? Therefore, the necessary condition is, with the resources available to you, you should be able to serve at least one of the requirement. Then you will get more resources, and then you might keep on breaking the deadlock, right? Otherwise there will be deadlock. That is the necessary condition, right? Then what is the sufficient condition? Sufficient condition is, if all the needs put together can be satisfied with the 4, right? Then that is sufficient, isn't it? If total needs put together is going to be satisfied by just this one, then that is sufficient, right? Okay, anyway, they are asking only about necessary conditions. Later we shall see what is necessary and sufficient conditions in detail, but let's focus on this question. Now what is that they are saying is, there are I processes, P1, P2, so on, Pn, n processes, and now each process has already taken up some resources, and then they want some resources, right, like this. They are saying that there are processes like this, P1, P2, P3, so on, Pn, okay, and now each process has already taken up some resources which are x1, x2, x3, x4, and again they are asking for some more resources which are y1, y2, y3 and yn. But then there are only two processes, there are two processes somewhere here, one is pp and pq, and these two processes are saying that we don't need any more resources, 0 and 0, right? But then they are holding xp and xq, and all the resources are completely over, which means if you add all these x1, x2, so on, they are all going to sum up to r is the total number of resources available, right? Now if you have to satisfy all these needs, I mean, in case if they don't, if you want to make sure that, or if you want to have some condition in such a way that we could avoid the deadlock, then once this pq and pp finishes, you are going to get xp plus xq, xq plus xp resources available at your hand. Using these resources, if you are able to at least satisfy the needs of one of the process, then you can keep adding more resources to the pool, and then you can keep breaking the deadlock, or you can keep satisfying all the processes. In case if these two processes put together, or these two resources put together, they are not even able to satisfy the minimum request, then they will not satisfy any of the requests, and all these processes are going to fall in deadlock. Only these two processes are going to come out. So what is the necessary condition for this process to come out of the deadlock? These two resources added together should at least be able to serve or satisfy the need of one process. And what is that process? I mean, we should be able to satisfy the need of at least one process. Which process that is? It is better that you take this process with the least amount of requirement, with the least requirement. Therefore, these two added together should be greater than or equal to minimum of yk, right? And then you don't put p and q there, which means I is not equal to p or q. This is the necessary condition. If this condition is satisfied, you can surely use these two resources to satisfy the request of some process, minimum of, let us say, yk, okay, and k is not equal to p comma q. So find out the minimum request and then try to satisfy it. Then that is going to give you some more resources, and then using it, if possible, you can satisfy the request of this need of other process. If that is not happening, which means if you are not able to satisfy the need of at least one process using this, then definitely you are stuck in deadlock. But if you are able to satisfy at least one need, there is a chance that you might come out of the deadlock. Therefore, it is just a necessary condition and not the sufficient condition. What could be the sufficient condition? Using these two, xp plus xq, if you are able to satisfy the needs of all the process, that will be a sufficient condition. Which means if xq plus xp is greater than or equal to sigma yi, all the needs, then you can say that clearly everyone can be satisfied using all the existing resources in any order. Therefore, there will be no deadlock. That is sufficient condition. But necessary condition is you should be able to satisfy the need of at least one process. And what is that process? The process which contains which requests least number of resources, which means the minimum request, the smallest request. Got it? So anyway, I don't know if you understood this or not, but what I'll do is, with more examples later, there is Banker's algorithm. Once I finish it, it will be very clear. Okay, just hold on for some time. This will be very clear. So what is the answer here? This one. Using these two, you should be able to satisfy the needs of at least the minimum one, right? Fine.